What is the fastest moving thing in the universe? That we know about, of course? It's light. Its speed in a vacuum reaches 186,000 miles per second. If people could travel at such insane speeds, we would have already explored hundreds of new worlds which are inaccessible to us today because of how far they are located. Interestingly, while traveling at the speed of light, you would experience time differently. Your mass would become infinite, and you would slow down. That's because the faster an object moves, the more mass it has. That's why, in real life, traveling at the speed of light in the conventional way doesn't seem possible. Okay, another question. Could we slow down the speed of light? In 2015, a team of scientists from Scotland claimed they had found a way to do just that. They sent protons through a special mask, altering their shape. And in this malformed state, super tiny particles of light started traveling way more slowly than regular protons. It's true that the difference in speed was almost imperceptible, but the fact they had managed to do it was amazing. It means that the speed limit of light isn't as unchangeable as we thought before. It's another question why anyone would want to slow down light as if it's not slow enough as it is. Ah, I see. This last statement might sound confusing, but let me explain. We humans are used to traveling at unhurried speeds of 60, 70 miles per hour on the highway. So to us, the speed of light seems to be unreachable. But how about this? If we reduce the observable universe to the size of our planet, crossing the Milky Way galaxy would be like walking a few houses down the block to visit your friend. And still, it would take a whopping 100,000 years if you traveled at the speed limit of this Earth-sized universe. This example shows how incredibly slow it would be for a spaceship to explore other worlds at the speed of light. Crossing our home galaxy would span more than 100 human generations. And even if we let humans be and concentrate on protons dashing across the solar system, the speed of light would still turn out to be too sluggish. Astronomers have calculated that it takes light almost as much as 45 minutes to travel the distance between the Sun and Jupiter. And it takes light 5 hours to reach Pluto. When you look up at the sky at night, you see stars as they were a long, long time ago in the past, thousands of years. That's how long it takes the light they emit to reach us. So now that we know that the speed of light is indeed pretty slow, we can try to find the answer to the main question. Why is it so? So far, the only answer astronomers have is because. A tiny bit more satisfying version of this answer sounds like this. The universe is designed in such a way that protons move with such velocity. There's no specific reason why it should be this way, it's just the way it is. As you see, the answer is a non-answer at the same time, and we're simply stuck in this slow universe. But would it be better if light was much faster? What would our lives look like if the speed of light was boosted by a factor of 1,000? Then, a spaceship moving at the speed of light could cross the Milky Way in less than a century. A trip to Alpha Centauri, the closest star to Earth other than the Sun, where potentially habitable planets may dwell, would take less than 2 days. Computers and different networks would function way faster due to enhanced optical speeds. But at the same time, the Sun would also become much hotter, around 1 million times hotter. And it would mean only one thing. Earth would be boiled in no time. So we should probably be grateful for our slow speed of light. If it were even a bit faster, our planet wouldn't exist.
So, what would it look like to go around Earth at the speed of light? Well, I'm guessing pretty quickly, but let's get to the details. Traveling around Earth at the speed of light would be an astonishing sight to behold. If we could magically achieve such a feat, here's what it would look like. As you kicked off your speedy journey, everything around you would get blurred. The landscape would transform into a streak of dazzling lights, like a cosmic fireworks show on Fast Forward. The world would appear distorted, with buildings and landmarks merging into streaks of brilliance as you zip past them. The familiar features of cities would become blur colors, blending together in a mesmerizing display. Day and night would blend seamlessly, since Earth's rotation would become an indistinguishable whirlwind. However, keep in mind that at the speed of light, time itself would behave strangely. To you, the journey might feel instantaneous, but when you return, you'll find that much more time has passed for everyone else. It's like taking a lightning-fast trip while the rest of the world ages. Sadly, achieving the speed of light is currently beyond our technological capabilities. Okay, but do you know what the speed of light actually is? In the vast expanse of empty space, the velocity at which light travels is an astonishingly precise figure. This translates to approximately 186,000 miles per second, a universally recognized constant notated as c, or the speed of light. Drawing from the revolutionary principles of physicist Albert Einstein's theory of special relativity, which forms the bedrock of modern physics, we come to a remarkable realization: nothing in the entire universe can surpass the velocity of light. According to this theory, as an object comes close to the speed of light, its mass spirals toward infinity. Consequently, the speed of light operates as an indisputable cosmic speed limit, casting its influence over the entirety of the universe. Such is the fixity of light's rapidity, yes, I have a thesaurus, that it finds purpose in defining internationally accepted units of measurement, like the meter and mile. The United States National Institute of Standards and Technology reveals that the speed of light even contributes to the definition of the kilogram and the temperature unit known as the Kelvin. Now, let's talk about the speed of dark. Darkness, the elusive counterpart of light, seemingly travels at the speed of light itself. In reality, darkness doesn't exist as a distinct physical entity, but is rather the absence of light. Whenever you block out a substantial portion of light, like when you cup your hands together, darkness fills the void. When discussing speeds, we can think of darkness as what emerges once the light ceases to illuminate, and it appears to move at the speed of light. Still with me? Yeah, my brain is starting to ooze out my ears too. Anyway, let's take a journey to distant space, far away from any light sources, such as the radiant sun. Imagine having a light bulb attached to the nose of your spaceship, emitting its luminosity in all directions through space at the speed of light. Now, if you momentarily turn off the light bulb and then turn it back on, a fascinating phenomenon occurs. Light continues to travel outward in all directions from before you dim the bulb, and subsequent light beams follow after you restore its glow. However, amidst these expanding spheres of light, an intriguing region emerges. It's the space in between there was no light because none was generated during the brief period when the bulb was off. So, in this cosmic spectacle, darkness appears to join the journey alongside light, seemingly chasing it at the speed of light. It reminds us that even in the absence of light, there is an enchanting interplay between shadows and illumination, each playing its unique role in the vast tapestry of the universe.
The speed of light is the fastest thing in our universe. It travels across space, passing through Mercury and Venus to reach us, and it's slowing down. No need to panic though. The sun is getting weaker, but we won't see the effects of it for another billion years. In the vacuum of space, the speed of light is around 186,280 miles per second. Any slower than that, and humans would see the changes firsthand. There would be some awesome effects, like colors changing and the brightness of objects fading. We'd also notice some differences in everyday objects, their length and shape. Scientists created a simulation to see what would happen if the speed of light was slower. In a vacuum, the speed of light can't change, but if light passes through different materials and objects, it alters the way we perceive things. Light acts as a wave and a particle, meaning that it's a wavelength. The color and frequency are determined by the distance from crest to crest in the wave. It behaves similar to sound with the Doppler effect. Imagine you're standing in the middle of a busy highway and a honking car speeds through. Wow, that was loud. You can hear that whoosh-like sound of the horn because the moving object produces the sound while you're stationary. The frequency and pitch seem to change. but it's just the sound reaching your ear faster than it would if you and the car were both stationary. Light behaves similarly. The wavelengths change if the speed changes. Moving toward a light source and making the wavelength shorter will shift the color to a blue and violet hue. Moving away from the light source, and you'll get something more reddish. So if the speed of light slowed down to walking speed, we'd notice the colors changing when we approach an illuminated object. At the same time, the color would change around us and behind us. If you walk sideways, the colors you're walking toward would become bluer, and everything in the distance would become red. This information is useful to astronomers who are studying objects in space. If they're blue shifted, that means the object is moving towards us. And if it's red shifted, then it's going in the opposite direction. In fact, everything in the universe is red shifted, proving that the universe is expanding and getting further away from us. The slower it gets, the brighter it becomes. That's because the photons become more present for us to see. At this rate, we can see invisible light and increased intensity. You won't notice that effect much if you're standing still, but because of the Doppler effect, moving towards an object will have different colors and different light intensities. Another phenomenon we'd experience is time dilation. It's when you move at a similar speed as light and time decreases relative to someone who isn't. Space and time are relative. So if you're sitting at your desk wasting hours away, yeah, sounds familiar, doesn't it? All your movement will go through time and not through space. You're stationary, but you're still technically moving forward in time, slowly aging. The faster you move through space, the slower your movement through time will be. If you move at the same speed as light, then all your movement will be through space and not through time. To notice that, you'd need another person to watch you. You're not in a time machine. You're both on Earth, experiencing the same time flow. To you, experiencing this firsthand makes it feel like you're going faster, because you're getting a lot more movement in space in a given time. The closer you get to the speed of light, the smaller you become. Well, not really, but it depends on who's watching. If you're the one traveling at such a speed, an object nearby will seem small, just as someone who's watching you travel at the speed of light will think that you're smaller than you actually are. The simulation that the MIT scientists conducted showed that if the speed of light drops, everything will become stretched out like a pancake. If you see mountains in the distance and then run at the speed of light, they will appear further away. Objects will become distorted, and it will feel like you're getting to a certain place faster because time has slowed down for you. If you're standing completely still and someone standing on your left-hand side throws a cube-shaped object over to your right-hand side, then naturally, you'll see one side of it unless it flips around. But in this new reality, you'll get to see the front side wrapping around the visible side you're seeing. If you're moving at the same speed as light in an infinite space, everything will be stretched out as you reach infinite speeds. In a world where people can walk at the same speed as light, we'll perceive nothing as normal. We'll have to get used to the way we see objects. Every movement we make will result in drastic shifts of colors. Even turning your head to look at something will feel weird. Let's say you're in a supermarket buying groceries, and you walk from aisle to aisle. The milk at the end of the counter will look like it's really close to you. But when you approach it, you'll start to feel like it's getting further away from you. The milk will also look a bit red. As soon as you get closer to it, it will shift to blue. If someone is passing through with a shopping cart, you'll see it as a sort of 3D model of a shopping cart. The color will shift as it gets further away from you. It will appear far away, but it's right in front of you. In fact, we don't really know the actual speed of light. Physicists gave it roughly 186,280 miles per second, but that constant is just for them to calculate other scientific stuff so we can understand it better. The problem is that we can only measure light with light beams and mirrors. But it's not like all we have to do is point a light beam at a mirror and measure its original path and its reflected path. Einstein's theory of relativity states that the original path of light moving from the source to the mirror may not be the same speed as the reflected light from the mirror back to the source. Hypothetically, If it takes light 10 seconds to travel from the source to the mirror and then back to the source, then we can conclude that each trip takes 5 seconds. But Einstein's theory is that it could take 9 seconds for light to travel from the source to the mirror and only 1 second from the mirror back to the source, or vice versa, or maybe completely different numbers altogether. That's why it's so difficult to measure light. A breakthrough came out for scientists when they managed to slow down the speed of light to 0 without losing its brightness. They did this by using ultra-cold atom clouds made with photonic crystals. These crystals are materials punctured with billions of tiny holes where light can refract. But what if we lived in a world where light stopped halfway? You'd wake up one morning and feel like it's twilight. You'd open the curtains and see that many car lights are on, but aren't so bright. You turn on the lights in your room, but feel like the bulb is tapping out. You replace it with another one, but it doesn't do the trick. You turn on the lights everywhere in your house, but it's all just giving weak light. You're confused and try to check if there's a problem with the electricity in your house, but it seems to be working well. You check on your neighbors, and they also have the same problems. Even experts in the field can't understand what's going on. Hours pass, and it's all the same. All the light in the world seems to have frozen halfway. Your phone is low on brightness, even though you bumped it up to maximum. Everything is getting darker. You learn from the news that it's a global problem. Light is slowly diminishing, and soon there won't be any of it in the world. You decide to wait it out while everyone else is panicking.
Whoa, something doesn't feel right. Everything seems shaky. It's definitely not an earthquake, and it's actually getting worse. The clouds seem to move quicker than usual, and the animals are going into a frenzy. The news anchor pops up on the TV in an alarmed tone and says, "Good morning. We're sorry to interrupt your program. Scientists have just discovered that the Earth's rotation has been fluctuating at an unusual rate. A group of specialists believe that the Earth is increasing its rotation with every second, and they don't know why. Even if the Earth increased its speed by 1 mile per hour, the day would only get shorter by a minute and a half or so. We wouldn't really feel it, and you could go on like nothing is happening. But as the Earth spins faster, our bodies, which are adjusted to a 24-hour timing, will have a hard time trying to cope with it. If you live by the equator, that means the rotation of the Earth is going quicker than at the North and South Pole. The area by the equator needs more time in order to complete its full rotation from the starting point. You'll experience more rain than usual. The Earth's rotation keeps the weather consistent and balanced so that nothing abnormal happens. But because the Earth is moving so fast, the weather is acting up. We'll start to see more storms and more cozy days inside, sipping on hot cocoa. Even though it seems weird, everyone can go about their day. But if the Earth picked up some speed and moved at 150 feet per second, the day would be reduced to only 22 hours. It kind of makes you feel jet-lagged 24/7. Every business works with the 24 hours a day schedule, so taking away even 2 hours can have catastrophic effects on the world economy. The whole calendar will have to change and adjust to the new timing. Clock designs will change with the new midnight, replaced with 10 o'clock. And with each week, the hours will shorten, so there will be no proper way of telling time except by sunsets and sunrises. The weather will continue to get worse and worse, feeling like the rain will never stop. The animals that rely on weather patterns won't know how to function, and mass migrations will occur from almost all species of animals. Flocks of birds will be flying everywhere and reach places they normally won't go to, affecting the whole food chain and ecology. Woods, jungles, and other places where animals roam are kept in proper balance when unaffected by humans. If it constantly rains in certain areas, then floods will force animals to move to other territories and compete with the predators in the area. If the Earth picked up speed every day, then standing on a scale in the Arctic would tell you weigh 180 pounds. But around the equator, you might weigh about 179 pounds. That's because of the extra force opposing gravity in that area. With the Earth spinning faster, all airlines around the world stop, since the radar systems have gone haywire and the weather is too dangerous to fly. Everyone has to get around by car. Satellites are positioned in such a way that it's crucial they remain where they are in order to bounce signals to us. Because of what's happening, Wi-Fi and TV signals can't go through. Communications around the world will end up short and slow, and eventually we'll have a total communication blackout. Ships will cease to operate and global trading will collapse, adding extra damage to the already failing world economy. Winds will get stronger and faster than usual, which means temperatures will change. Storms like hurricanes will be stronger than ever and have more energy for destruction. And still, at 100 miles per hour, the equator will now be swallowed up in the water. The Amazon basin and small islands will now completely submerge in water by around 50 feet. Most of the plant life will be in danger, especially by the equator. With woods threatened by floods, more animal environments will be in jeopardy. The trees and plants won't survive so much flooding. If the Earth rotated so fast that the hours would now be reduced to 15, then we'd probably feel like we're always on a jet plane going through turbulence. It would be impossible to sleep if the Earth kept picking up speed every second of the day. So days would be around 7 hours long as well as nights. The whole world would be flooded, except for the highest points and the tallest mountains. If that happens, humans will most likely end up there clinging to the last remaining clear patches of land. Most of the animal life will be extinct as well. And as the Earth is spinning faster and faster, the crust will lose its durability, allowing more frequent and stronger earthquakes to happen. Volcanoes will erupt all over, even if they're submerged in water. It'll go on like this for quite a while. Many major natural disasters like earthquakes, tsunamis, volcanoes, and even melting ice sheets have sped up the speed of the Earth by milliseconds. So, with the Earth's continuing speed increasing, these natural disasters will make the planet go even faster. Even if it's just for milliseconds, it's enough to have major consequences. The Earth is now spinning at 1,000 miles per hour. And as you're sitting with the rest of the survivors, you feel yourself levitating slightly. You'll see tiny pebbles and rocks floating inches from the ground. The clouds above you are passing like shooting stars. The air is thick with moisture, since water is rising to the top, forming thick clouds ready to pour. But since gravity is weaker, some of the rain is suspended in the air. Many small objects will be floating around as if you were in space. The days and nights won't be longer than a few hours. At this point, the whole world will be flooded and the crust will be 80% gone. If it goes on any longer, there won't be any living things around, probably except for microscopic creatures that can withstand extreme and harsh conditions. The Earth would need to spin at approximately 17,600 miles per hour to cancel out the gravity for things to start floating around. At this point, all the water in the ocean will rise and look like reverse rain. The large mountain rocks will separate from the bedrock and levitate above the ground, looking like little planets in space. The Earth is now spinning 17 times faster than usual, which makes one full rotation around its axis only 84 minutes instead of 24 hours. If you manage to stay that long, then you'll literally see the days and nights go by in an instant. You'll also be floating aimlessly in the sky, bumping into rocks and other surfaces. You won't recognize anything anymore. The Earth's crust is ripping apart, exposing the magma underneath. So landing on the ground isn't an option. You'll see outer space as you go higher and higher. You won't know how fast you're going, but all you know is that you're probably the only human left in this spinning world. The Earth will eventually spin so fast that the rest of the layers will start to peel off, exposing the Earth's interior. It'll start to squeeze itself from the core until it becomes similar to a pancake. Nothing can survive at this point. So much heat will be produced from the core that the planet will heat up like a microwave. All the water will disappear, and it'll look like a red dot in the solar system. And once it starts to approach the speed of light, time will freeze. The rocks and floating elements won't move and will eventually be distorted. And with enough effort, the Earth will eventually turn into a black hole. Of course, nothing like this will ever happen. According to scientists, Earth will most likely slow down in rotation. Ever since the Moon came into the picture, the Earth has been slowing down by around 4 miles per hour every 10 million years or so. That's because of the Moon's gravitational pull on our little blue planet. It'll most likely go on that way. So hey, what's your hurry? You switch on the light as soon as you enter a room. You never even stop to think about counting how long it takes for the bulb to light up. You couldn't. It's as if it's instant. Well, technically you could if you were fast enough. Good luck clicking that stopwatch in time when you're measuring over 670 million miles per hour. That's 180,000 miles per second. Almost the distance from the Earth to the Moon in the snap of a finger. Oops, wrong sound effect. Can you give me a finger snap? Yeah, that's it. In the snap of a finger. And the Moon's further away than you probably think. If all the planets in the entire solar system were lined up in one epic conga line, they'd fit between the Earth and its satellite. And that's including poor outcasted Pluto. Okay, light is fast. Moving on. It's a beautiful sunny day, perfect for a jog. And like any other day you go for a run, you stop and think, hey, I wonder what the speed of sound is, don't you? Well, definitely not nearly as fast as light. Need proof? Check for yourself next time it storms in your area. You'll see lightning flash before hearing the crack of thunder. The light from that bolt rushed to you, zoomed into your eyeballs, and up into your brain for you to understand, oh, lightning. All the while, the sound wave from the thunder is still on its merry way to your ear. It'll get there, just give it time. By the way, thunder isn't the sound of storm clouds crashing together. It comes from that very same lightning bolt. It races toward the ground and rips a path through the air as it does. The air politely moves aside to make way for the lightning, and in the instant the lightning's gone, boom! The air comes back together and makes the sound we call thunder. Oh, and here's a fun fact. Sound travels faster underwater than in the air. A little over 4 times faster to be exact. So if you were to go for a swim with your friend and shout something bizarre underwater, they'd hear it a bit sooner than if you did the same thing outside of the pool. Uh-oh, everybody else heard it too. Oops. Sound also travels over longer distances underwater. It's why humpback whale calls can be heard for thousands and thousands of miles. But in a controlled environment where the air is dry and we have a constant temperature of 68 degrees Fahrenheit, the speed of sound is about 760 miles per hour. Now, that's a more realistic number, one that people can even reach. The famous Bell X-1 aircraft was the first to break the sound barrier on October 14, 1947. Test pilot Chuck Yeager was in the cockpit of the rocket plane. Imagine hearing that sonic boom for the first time ever in history. Bravo, Captain! Humans can race with sound, but light is a whole different challenge. For one, measuring it in the first place is no easy task. The official speed of light has changed several times throughout history, even going back to the 1600s. After centuries of debate and experiments with different results, the scientific community finally settled the matter in 1983. Maybe. To measure the speed of anything, you'll need to know 2 things: the distance between point A and B, and the time it takes for an object to travel between those points. With distance divided by time, you'll have yourself the speed of light. But with every experiment done to measure light speed, there's always been an extra cog in the wheel that everyone overlooked, or rather brushed aside. When doing an experiment using light beams and mirrors, we've always included the light beam's trip from A to B and back to A. With equal speed and equal distance, we have ourselves a controlled experiment and conclude an official speed number for the books. Case closed. Let's celebrate! Not so fast. A certain someone in 1905 had something to say about this, and that someone put a theory out there that light can travel different speeds going forward and back. Still can't wrap your head around it? Well, let's take this example. You had a long day. You pulled an all-nighter at work and can't wait to sink into your comfy warm bed. You get on a bus and head home. The night's clear and there's zero traffic on the road. Before the wheels on the bus can even go round and round, you immediately conk out in the back seat. But right before that, you checked the clock and saw it's exactly 10 p.m. What? After a big bump on the road jolts you awake, you become aware of your surroundings. But you suddenly find yourself in the exact same spot as the moment before you fell asleep. That was a quick nap. But then you look at your watch and it's now 11 p.m. You fell asleep in the bus and missed your stop. You'll have to repeat the exact same route all over again. Bummer. What can you determine from this? Since the whole ordeal took you an hour, you can assume it took exactly 30 minutes from the bus stop to reach your house and another half hour from your house back to the bus stop. Sounds logical, right? In our physical bodies, such a conclusion makes perfect sense. But it was Albert Einstein who challenged this idea. With his reasoning, the trip could have taken 59 minutes to get home instead of 30 and 1 minute back to the bus stop. Or even vice versa. Since you were fast asleep, there's no way you can know. And this idea is what's keeping scientists and physicists up all night throughout the decades. When you get into light speed in space, then the mind-blowing stuff starts happening. It takes approximately 8 minutes for light to reach Earth from the Sun. So, light is super slow in space? Not really. Now we're talking unimaginable distances. It takes 8 minutes for our sun's light to travel over 90 million miles to our planet. That's something to think about when going to the beach. The sunlight that made your tan lines traveled so far across our solar system to reach your skin. Ah, how thoughtful. And you can get sunburnt even on a cloudy day. That's how powerful our star is. Now, imagine yourself living on Pluto. I know, its planet membership got revoked in '06, but hey, call me old school. Our former furthest planet from the sun is so far away, it takes 5.5 hours for sunlight to get there. No wonder it's always cold. The first planet in line is Mercury. The sun's rays reach it in a mere 3 minutes. Hey, that's probably enough time to listen to your favorite song. By the time the song ends, you, the Mercurian version of you, will be basking in the sun's glory. It'll be impossible to listen to that track in space since sound can't even travel out there. No one can hear you scream. Oops, there she is again. Music is just vibrating air, and without any air in space, sound can't travel. That explains why it's so eerily quiet out there. Okay, can somebody take the scream girl down the hall? And while we're up in space, let's pay our neighbor a little friendly visit. Alpha Centauri is the closest star system to our own. And what fun, the trip is just 4 light-years away. That's 25 trillion miles and 137,000 years on the road. Yeah, don't forget to pack a big lunch. To put all that in perspective, it would take around 5,000 generations in a super shuttle traveling through empty vast space to complete the journey. And we won't be able to come close to the star. Oh, and that's just one way. Okay, I think I'd rather come back to Earth now. Whew, that's better. Now, the longing question: how can we measure the speed of light without that little dilemma about the return trip? Oh, I got it. Why don't we just measure the speed with a super high-tech camera and map it out frame by frame until we're able to write down its speed? Well, nothing's as easy as it seems in the world of physics. Because when filming the light through a lens, we're not seeing the light itself, but rather a reflection of it. We just circled back to square one. Okay, scratch that plan. Then how can we prove light is going the same speed to its destination as its reflection is back to point A? Does the one-way speed have a defined value that's not a constant? Well, this is the ultimate question among scientists, and so far, there's just no way of truly measuring it. Unlike the speed of sound, which is more conceivable, the speed of light might just be light years ahead of us. Yes, just more fun light facts brought to you by The Bright Side. See the tie-in? Okay, never mind. Cold and seemingly infinite expanses of the Arctic. The white of the snow is blinding. In this vast and empty space, there's a dark dot. Getting closer, it turns out to be a small research station. One door and one window. An old antenna on the roof wobbles from the strong winds. You're sitting inside this hut in warm clothes, drinking hot tea. An electric generator hums under the table. It's connected to a TV and game console. You take the gamepad and select the video game you want to download. It's about 650 gigabytes. It seems in such a place it will download over several centuries. But you press the button and the game is downloaded on the console in less than a second. Welcome to the world with the fastest and most accessible internet. The internet already works at the speed of light. Phones use a specific frequency of radio waves that travel at the speed of light. You're watching this video using the internet at the speed of light. Most of the data is transmitted through a copper wire or fiber optic cable. This happens so fast that we won't notice the difference whether it's transmitted at the speed of light or not. Wi-Fi also uses radio frequencies to transmit signals between devices. The fact is that the speed of the internet is not about how fast a file travels from one device to another. It's about how much data is transmitted over a certain time. So, let's imagine that data of any size can be loaded at the speed of light. 300 gigabytes of several movies in 8K, 400 gigabytes of a video game with ultra-realistic graphics, 1 terabyte of a project for a graphics editing application, and all of this is downloaded to your device in 1/100th of a second. The internet is a connection between computers. For everything to work correctly, the computers connect to a router. This thing works as a controller. It makes sure that the message from one computer reaches the other without any confusion. When there are too many computers, you need more routers that connect to other routers. You can scale this network indefinitely. To connect millions of houses to the network, developers can use telephone cables. To make this complex system stable, it's served by internet service providers. They're companies that we pay money to access the internet. In simple terms, all information from the internet is transmitted via a cable directly to the Wi-Fi router. It uses radio waves to wirelessly transmit data to a computer or phone. Your devices are also equipped with an antenna that can catch and transmit signals via radio waves. The speed of the internet slows down when it goes through different routers, receivers, and other technical hurdles. The cable may be damaged. Providers limit the speed intentionally and increase it when you pay more money. Also, the speed of the internet is affected by the number of users connected to the same network. It's like a broad highway with a traffic jam. The more cars there are driving on it, the slower they move. Just like that, your data is loaded onto your devices. To spread the internet at the speed of light everywhere, developers need to improve cables data passes through. The number of networks and routers should be increased. The jammed highway will become even broader, and cars will be able to drive at full speed. Providers should remove all restrictions as well. Every mobile device and computer should have a high-frequency antenna that catches signals from an ultra-fast router. Several huge routers are located all over the planet. They look like enormous boxes without windows and with giant antennas on their roofs. Deep underground, thick cables providing ultra-fast data transmission are connected to these boxes. As soon as the signal from the cable enters the box, it broadcasts to space via radio waves. Thousands of satellites hover over the planet and intercept these waves to spread them throughout the world. So, anytime and anywhere, you have access to the internet that's working at the speed of light. Movies and video games are created several times faster. A lot of time is spent trying to transfer a terabyte of data with graphics from one computer to another, which is located in another country. Now, with Super Internet, developers get any amount of data in an instant. Flash drives and hard drives are no longer needed in the world. Everything is kept in cloud storage. From there, you can download any file to your computer thousands of times faster than if you downloaded it via USB. Companies that provide cloud storage services are becoming the richest in the world. You have access to the internet in the elevator and the subway, in the mines deep underground, and among the hot sands of the Sahara. The phones are released without internal memory and with an incredibly cool camera. You can record an infinite number of videos with 16K quality and not think about where to store them. You can do color correction, develop games, or edit your videos all on your phone. You don't need powerful processors for such operations. Everything works with the internet. You remotely connect to a powerful computer and work from anywhere. That's why the market for expensive computers has collapsed. Nobody wants to spend money on a cool graphics card because a new one will be released in a year. It's much easier to connect to the computer where it's already installed. Even in our time, such companies already exist in great numbers. You can play a new video game on top of settings on your old computer or phone if your internet connection is fast enough. Super Internet creates a perfect climate for the rapid development of modern technologies. Virtual reality lenses, for example. On an airplane, in a submarine, in the desert, you can watch the highest quality movies in 360 or play games with augmented reality. Special effects and graphics in such games become indistinguishable from reality. Artificial intelligence can process data from all over the world simultaneously, in seconds. Thanks to this, people make discoveries in the field of medicine and genetic engineering. Scientists are developing a machine that can upload the human mind on the internet and download it back. Each user's cloud storage accumulates so much digital garbage that people hire special companies to clean up terabytes of useless data. A huge amount of energy is consumed. It provokes an increase in the price of electricity. To save money, people build small wind farms in their backyards to generate electricity. Many people make tunnels to get to underground rivers. Using special equipment and a powerful water flow, you can create a home hydroelectric power plant. The roofs of most houses are covered with solar panels. The internet is becoming as familiar to the world as the air. There's no longer a place where you can't connect to the web. Some vloggers put a phone in a box made of refractory metals and threw it into the mouth of a raging volcano. Even then, the connection wasn't broken until the phone melted. In a few years, the data on the internet as a whole increases thousands of times. Billions of petabytes must be stored somewhere. Developers around the world build data centers to support cloud storage. They appear underwater, underground, in the mountains, and even in forests. Scientists understand there won't be enough space for such data storage in the future. In addition, all centers emit strong radiation, which is bad for humans and the Earth's atmosphere. Therefore, the world's IT companies unite to create a giant data storage server in space. They build such a station in the orbit of our planet. Developers install special equipment there to ensure the operation of cloud storage. Every year, the station grows in size. It receives energy from solar panels. After a few decades, the data center becomes a cube half the size of Earth. You can look out the window and see its outline in the blue sky, better than the moon. At night, millions of light bulbs glow on it. An enormous area on the moon is covered with solar batteries to provide the cube with additional energy. Now it looks like a disco ball. Humans colonize Mars and take the super internet there. Now you can make a high-quality video call to a friend who is on the red planet.
Something's moving toward our planet that could end all life on Earth. It's a regular needle, weighing about 5 grams. You're probably wondering why it's so dangerous. Can something that small really do any harm? It's hard to say, because it's moving at the speed of light, and we don't really know what will happen when it hits. That's because the idea itself is hypothetical, so it leaves us with a bunch of questions. Here's the first one. What happens to a sewing needle in space? Could it actually accelerate to the speed of light? The short answer is no, but it's not that simple. In our universe, nothing that has mass can reach the speed of light. It takes energy to make any object go faster. Since there can't be an infinite amount of energy, nothing can ever accelerate that much. So in our case, we can simplify things. Let's say that the needle is moving at 99.9% of the speed of light. That's about 186,000 miles per second, or 670 million miles per hour. At this speed, the journey from the Earth to the Sun would take about 8 minutes. For comparison, the maximum speed of a Falcon Heavy rocket is 24,600 miles per hour. And the fastest car on Earth is more than 2 million times slower than the speed of light. The biggest rock to ever hit our planet was the Hoba meteorite. It weighed about 60 tons. It fell to Earth around 80,000 years ago and caused a lot of damage. Would something as small as our sewing needle be able to have the same effect? Sure it would. It's all about the energy involved. Small things traveling at almost the speed of light would have more energy in them than really big but slow-moving objects. So our speedy needle would hit the ground much harder. On impact, all the energy it contained would cause a mighty big kaboom. Everything nearby would just disintegrate. But could such a big explosion really destroy our entire planet? Let's compare this to the biggest blast humans ever made. The cloud of debris that followed this explosion was 40 miles high. It could be seen from a distance of 100 miles. About 50 megatons of explosive force was released into the atmosphere. The energy our needle would release as an explosion would be about 43 kilotons of force. That's less than what humans can cause, but it could still lead to massive damage. So if you hear on the news that something is headed for Earth at the speed of light, you'll definitely need to find some cover. Could people survive a collision like this? Well, it would be pretty scary. A dazzling flash of light would be followed by a shock wave of incredible force. The glass in all houses within a 2.5-mile radius would be smashed. Even the strongest buildings would collapse. All that energy coming from our needle would cause seriously big fires up to 1.5 miles from the epicenter. Everything at this spot would essentially be vaporized. The situation would be a little different if the needle went into the ocean. Just like a meteorite, its impact would cause a huge tsunami, but the shockwave wouldn't affect big cities, and people probably wouldn't be hurt. Although if it hit off the east coast of the United States, this tiny object could still cause flooding in New York. But other things could happen if a needle like this entered the Earth's atmosphere. Because it's moving close to the speed of light, the needle won't actually be a solid object anymore, but more like a bunch of atoms flying alongside each other. So it's possible that the needle would just pass right through our planet, the same way it would cut through a balloon. It would happen very quickly, in a split second. No one would even notice, and people would just go about their business. But here's the most incredible possibility. What if the needle hit a person? Well, there's a very small chance of that happening, just 1 in 1.6 million. Although something similar happened at least once, when 2 men in Turkey experienced rain made of rocks in 1888. But let's get back to our needle going at light speed. If the human body completely absorbed all that energy upon impact, it would just disintegrate. But there's another possibility as well. The needle could weaken the bonds between molecules and atoms in your body and pass right through them without causing any pain. You'd just feel something like a mosquito bite. Of course, it would still leave its mark. The needle would make a perfect hole in your body, but so long as it didn't go through your vital organs, you'd be fine. Plus, you could boast about your incredible good luck. The chance of a space needle hitting you is almost like winning the lottery. So it seems a needle moving at light speed wouldn't do that much harm. It might create a big crater in one spot, but the world would be all right overall. But what if something much bigger than a needle flew towards Earth? In 2013, a large meteorite entered the atmosphere above Russia. Luckily, most of it burned up before it reached the ground, but the largest piece of it that survived weighed slightly over half a ton. The meteorite exploded about 14.5 miles above the surface and lightly damaged more than 7,000 buildings. About 1,500 people were injured, but it was only moving at about 37,000 miles per hour. What would happen if it had accelerated to close to the speed of light? An object this big, moving at a speed of nearly 186,000 miles per second, would have an enormous amount of energy. Its impact would basically wipe out an entire continent. The blast wave would have such force that it would completely circle the planet and pull down absolutely everything in its path. The tsunami caused by the explosion would wash our civilization into the ocean. Humans would only survive if they made it to very deep underground bunkers. But once the dust settled and we went back up to the surface, we would find that there was nothing alive left on Earth. It would be more or less the same as when a meteor destroyed the dinosaurs millions of years ago. It's true that that meteorite didn't move as fast, but it was just as big. Of course, our planet recovered from that impact, and life returned. There is actually an object moving around in our solar system right now that could destroy half the Earth: Halley's Comet. It weighs about 220 billion tons. That's a whole lot of zeros. By the way, this comet has come close enough for us to spot it at least 30 times. The last time it could be seen was in 1986, but we'll have a chance to see it again in the not-too-distant future. Its next appearance is predicted for July 2061. If an object like Halley's Comet hit the Earth at the speed of light, it would completely change the shape of our planet. The blast would form a crater the size of Eurasia. After a blow like that, the Earth would never be the same again. Now let's talk about something that's a little more real, although it's seriously weird. Is there anything out there in the universe that can move at the speed of light? Well, almost. Scientists have discovered that some superactive galaxies can spit out hot blobs of gas the size of Jupiter. These galaxies are called blazars. When they studied the blobs, the scientists scratched their heads in confusion because the speed of these things is about 99.9% the speed of light. To accelerate something as big as a bowling ball to that speed would take all the energy produced on Earth for an entire week. So imagine how much you'd need to fire off a Jupiter-sized lump into space. The chances are that these blobs are getting all that energy from supermassive black holes inside the blazars. The hole itself absorbs tons of particles, but also accelerates others and pushes them out into space. The near future. Our planet is running out of energy sources, and the human population is growing. There's less free space on Earth every year. People have to move to other planets as soon as possible, but there isn't enough energy for spaceships and interstellar voyages. You're a member of a group of scientists searching for energy sources in the universe. Solar power, windmills, hydro, and thermal power plants. It's not enough. You offer an adventurous but risky idea. You want to create an object and accelerate it to the speed of light. This object will start generating infinite energy. Other scientists immediately reject this idea. Such an experiment can destroy the entire planet and even the solar system. If something moves faster than light particles, it creates a black hole. To reduce the risks, you suggest speeding up a small and thin object, like a simple needle. As soon as it reaches the speed of light and releases energy, special machines similar to solar panels will absorb this energy. Only 1 millisecond of moving at the speed of light will be enough for humanity. Then, the needle should be stopped. You suggest to slow it down with the help of Mount Everest. You want the needle to smash into it. As soon as you start working on the experiment, you face an unsolvable problem. An ordinary needle, like any other object with mass, can't reach the speed of light. According to the laws of physics, it's impossible. To do this, you need to turn the needle into a beam of photons. The metal of the needle will be erased into dust during acceleration to the speed of light. Earth's atmosphere shows strong resistance to a moving object. So now, you need to create the strongest durable material in the universe. It not only has to withstand the air resistance, but also not be torn apart by the energy growing in it. When any object increases its speed, its energy increases too. You need a lot of money to create such a needle. But before you get it, you have to conduct this experiment in a simulation program to prove you're doing the right thing. This program is a computer hologram of the solar system. The program imitates and visualizes all the laws of physics. You can run your experiment using this model, and if it goes well, you'll get money to implement your plan. So, you create a computer simulation of the needle. Then, you build a machine with an incredibly powerful engine. It works like a rocket. Several motors are attached to the needle. They help reach the speed of sound, then charge the needle with energy and release it. Using the charge force, the needle should accelerate to the speed of light and crash into Everest. You'd need to set the launch spot of the needle a long way from the mountain for the whole operation to work out. Air resistance greatly hinders the acceleration. The needle's path must pass through thousands of miles of free space. You decide that it's better to launch the experiment from space, where there's no resistance. To do this, you build a base on the moon in the simulation. Computers calculate the exact start time and needle position. You need to know the speed of the Earth's movement around its axis and the moon's movement around our planet. The slightest deviation from the course can cause the needle to crash into the ocean or a city. If it gets into the water, severe floods and tsunamis will happen all around the world. The computer calculates the ideal moment for the needle to fly. You're ready to start the operation. Scientists and presidents of different countries are watching the simulation. You're so nervous, you're sweating. You come up to the computer and press the start button. Everyone is looking at the big screen. A rocket with a needle placed on top flies up. It's rising high above the moon. It reaches the speed of sound. The first engine falls off. The rocket's mass decreases and its speed increases. Half the distance between our planet and the moon is gone. There's 2 engine turbines left. The speed of sound is exceeded by 10 times. The second engine falls off. The needle is approaching the Earth's atmosphere. The third engine generates a huge charge of energy, strikes it into the needle, and flies away. The needle turns bright red and hot like the sun. It penetrates the Earth's atmosphere. The protective layers of our planet can't prevent the needle from reaching its goal. The sky lights up with a bright flash. In the next half second, the needle will hit Everest at the speed of light. 2 seconds later, your experiment will fail. And here's why. The greater the speed of any object, the larger the mass and the amount of energy that accumulates inside. When the needle reaches the speed of light, its energy begins to increase indefinitely. The mass grows to infinity. And when this happens, a black hole is formed, a massive object with an incredible gravitational force that absorbs absolutely everything, even light particles, photons, and the time dimension. This is called the event horizon. Literally, everything that is an event, time, space, matter, is absorbed by the black hole. No one knows what is inside the black hole. After 1 millisecond, the needle almost reaches the speed of light. It releases a huge amount of energy into the atmosphere. If you look at it in slow motion, you can see how the air is ionized. That is, the air molecules are split. In nature, this process occurs during lightning flashes. Our sun also has ionizing energy and disinfects the air. The needle cuts through the Earth's atmosphere. The sky is lit up with a bright light. All the clouds and every water molecule around the needle instantly evaporate at the high temperature. The sky becomes crystal clear hundreds of miles around the spot. In the center of this clean circle is the needle, and it's approaching Mount Everest. Hundreds of thousands of tons of snow burn up as soon as the needle gets close to it. It has reached the speed of light. A thick layer of ground melts and flies away in different directions. It looks like someone has thrown a spear into an ice cream mountain. Everest can't handle so much energy and is torn apart into a million pieces like a sandcastle. The incredible power of the blast wave destroys everything around. Stone, wood, soil, leaves, concrete, everything falls apart into billions of pieces because of the powerful energy and heat. Then, all these molecules are erased. The needle moves faster than photons, and as soon as it overtakes the light, it starts to overtake time. From the needle's point of view, all events begin to go in reverse. The mass of the needle becomes infinite, and the greater the mass, the greater the energy. A burst of unthinkable gravitational force absorbs all space. Land, trees, nearby cities, the Earth's crust, and the core, everything disappears in a matter of seconds. A black hole absorbs light and time. An absolute black void has come. The black hole is growing. Holographic International Space Station is shrinking thanks to the strong pressure of gravity and is being pulled into a black void. Then it's the moon's turn. The force of gravity increases quickly. The hole is getting heavier and more massive. All the planets of the solar system collapse as the gravitational black giant grows. The sunlight goes in and never comes back. The black hole becomes thousands of times heavier than the sun. Our star splits into millions of thin strips of light, like spaghetti, and spits out powerful streams of energy. An empty sector of outer space with an expanding black hole is in the place where our solar system was just moments ago. Meteorites flying past it also fall into the trap. Just one small needle managed to cause such a disaster. The simulation ends. The program breaks down because it can't calculate further events. You realize it was a bad idea after all. You decide you'll try to get the energy from the Earth's core instead. Attention! Attention! Residents of all countries and cities of the world! A massive asteroid is approaching the Earth. Now its speed is several times greater than the speed of sound, and each day it accelerates even more. Once it enters our solar system, it will fly past Uranus, Saturn, Jupiter, and Mars. The gravitational fields of these planets will also accelerate the asteroid, and our planet will be the final destination. A collision is inevitable. According to scientists, a meteorite the size of Mount Everest can destroy the entire planet. The disaster will happen in 350 days. There's panic in the streets. People buy and build bunkers. Scientists and astronomers from all over the world were assembled to find a solution. The only way to avoid the collision is to destroy the space object. Yeah, a powerful rocket can split an asteroid into hundreds of thousands of pieces. In this case, a meteor shower will hit the Earth, but it's better than the complete destruction of our home. In less than a year, people build several powerful rockets. Then, using the best telescopes in the world, astronomers create a unique guidance system. And now, we just have to wait for the asteroid to get into our solar system. All the people start moving to one continent with top-notch bunkers for everyone. The damage from the asteroid is impossible to predict, so it's better to hide people in one super large safe place to wait out the collision. The moment has come. The asteroid passes by Uranus. The speed increases. Now the colossal space object moves only 10 times slower than the speed of light. Scientists launch rockets into the air. The asteroid flies past Saturn and destroys a part of its ring. The asteroid's trajectory is changing. It flies past other planets through a twisting path, picks up speed, and now heads towards the Earth. The rockets leave a long trail of fire behind and reach the speed of sound. They're getting closer to the asteroid. Near Mars, a collision happens. The rockets hit the target. The asteroid explodes and splits into millions of particles. All the pieces fly in different directions. The Earth is saved. At this moment, the Earth's satellites record a huge burst of energy. A small part of the asteroid is headed towards Earth. It's tiny, about the size of a grain of sand. But the explosion accelerated it, and now the grain of sand is flying towards the Earth at a speed of 185,000 miles per second, which is 99% of the speed of light. At this speed, the grain has almost the same destructive power that the entire asteroid had. It's approaching the moon. A few more seconds, and the grain of sand will hit our planet. All the people are waiting with bated breath. The grain gets such incredible power because of the laws of physics. The greater the speed any object is, the more mass and energy it has. When the grain of sand reaches a speed close to the speed of light, its energy and mass begin to increase dramatically. You can't even see this tiny grain of sand, but inside, it has the mass of an entire continent. If the grain reaches the speed of light, its mass will be infinite, and then a black hole will appear. In this case, all living and even inanimate things on the planet will disappear. Trees, seas, and oceans, all the cities, countries, and continents, air, sound, atmosphere, any molecule of the Earth. Everything will be absorbed by the incredible gravitational force of the black hole. Then, when there is no trace of our planet, the hole will take over the moon. The gravitational force will grow and absorb other planets of the solar system. Soon, it will reach the sun. Our star will split into thousands of strips like spaghetti and will emit a tremendous amount of energy. This could trigger the birth of a second black hole, but fortunately, we only have 99% of the speed of light, which changes everything. Also, no object that has mass can reach the speed of light. The grain of sand enters the Earth's atmosphere. From the outside, it looks like a blinding meteor that pierces the sky. The grain heats up, passing through the layers of the atmosphere. Clouds within a radius of 100 miles around are burning up. The sky becomes crystal clear. If you look at it in slow motion, you can see the air is ionized because the air molecules are split. In nature, this process occurs during lightning flashes. Our sun also has ionizing energy and disinfects the air. The meteorite leaves an ozone hole behind it. So now, this place is not protected from space radiation and ultraviolet light. The grain of sand flies straight into the center of the Southern Ocean. The closest continent to the explosion is Antarctica. The air around it warms up and mixes with the cold temperature of the ocean, creating hurricanes. As soon as the grain approaches the ocean surface, the water starts boiling. The temperature and energy of the grain are so huge that the water evaporates, but the vapor molecules are instantly burned up. Thousands of gallons of water just disappeared from the face of the Earth. The grain flies down for the first few feet without touching the surface as the water evaporates before it. Then it falls into the ocean and creates a powerful explosion. Hundreds of millions of gallons of water foam and boil because of the hot temperature. The entire ocean within a radius of 100 miles is illuminated with a bright light. The ocean depths, where sunbeams have never been before, are almost as transparent as the water at the bottom of a pool. The wreckage of old sunken ships splits into atoms because of the powerful explosion. Unknown sea monsters and giant squids that live in the dark are afraid of the bright light and swim away. Then, finally, a grain of sand touches the seafloor and penetrates deep into the Earth's crust. If it reaches the Earth's core, the planet will most likely explode from a burst of incredible energy. Fortunately, this is not going to happen. The resistance of the ocean and the ground slows down the grain and takes its energy away. It provokes a slight shift of tectonic plates, and there's more to come. Huge waves form and spread throughout the ocean. The blast wave creates enormous tsunamis. Imagine throwing a small rock into a puddle. The same thing happens to the ocean. Huge waves are approaching the coastal cities. Fortunately, people were evacuated from there, but the damage caused by one grain of sand will cost hundreds of trillions of dollars. Houses are destroyed, roads are flooded. After a while, it starts raining with hurricanes. Ocean water vaporized by the grain forms into huge storm clouds. The wind drives them to the continents. And then, after the tsunami, prolonged rain begins, flooding entire countries. Several days later, natural disasters are still here. The temperature of the Southern Ocean has increased by several degrees. The water is boiling at the collision site, melting the Antarctica glaciers. Millions of icebergs are melting away, so the water level of the world's oceans is rising. The edges of some continents go underwater forever. Thunderclouds reach the Sahara and other deserts. The shift of tectonic plates causes earthquakes on some continents. Volcanoes are awakening. The sky is filled with volcanic ash. It will take months for all the ashes to settle. In the beginning, it creates challenging conditions for life on Earth. Plants and all living things don't receive enough sunlight. In trees and seaweed, photosynthesis is disrupted. Oxygen production stops. It's getting harder to breathe. The air that has filled the planet's atmosphere is slowly running out. People have to adapt to new conditions. They build new cities both on the land and in the ocean. They create plantations with artificial lighting for photosynthesis production. Fortunately, all the problems end when the ash settles. Inside the volcanoes, there's hot magma flowing. It may come in handy as it's rich in chemical elements and minerals. Together with the ash, nutrients fall to the ground, and the soil is now well fertilized. Plants, trees, fruits, and vegetables grow incredibly fast and produce a lot of new oxygen. The Sahara is filled with blooming flowers now, and it looks more like a meadow with flowers, not a desert. The grain of sand just renewed the planet instead of destroying it. This is the final game of the year. Millions of viewers are glued to their TV screens. The 50,000 people in the stands of the stadium are holding their breath. Everyone's waiting to see who will win this game. It'll decide the winner this year. The loudest fans have stopped chanting. The air's become thick as syrup. It's so quiet, you can hear the heartbeats of the spectators. The pitcher looks at the ball one last time. He's taking wind speed into account and prepares to bring victory to his team. There's the throw. The ball flies like a bullet through the stadium, but the batter's reaction is perfect. And then, the incredible happens. The impact energy accelerates the ball to the speed of light. Okay, let's stop now. I've got to explain this. Nothing in the universe can reach the speed of light if it has mass. For a person, a car, a rocket, even a comet, that speed is out of reach. According to Einstein's general theory of relativity, when an object moves, its size decreases and its mass increases. If an airplane accelerated to the speed of light, its mass would be infinite and its length, 0. It's impossible. But living by the rules is boring, even if they're the laws of physics. I'm sure Einstein would love our idea. So, in our lawless world, the batter hit the ball and it flew at 186,000 miles per second. In just 1 second, the ball would fly around the Earth 7.5 times. Spectators, grass on the stadium, air molecules. Everything around is frozen. Only the ball is moving forward. The small projectile flies out of the stadium, rips apart the atmosphere, and goes into space. And then, the horror, the ball crashes into the International Space Station at full speed. The station has no chance. An object at the speed of light will blow away everything in its path. This story is impossible, not only because a baseball player's bat would break from such a blow. A small ball of leather and rubber will trigger a flash in the center of a stadium that is brighter than the sun. The bright light would be followed by a thermonuclear explosion. When the batter propels the ball to the speed of light, the show begins. The ball moves so fast that the air molecules don't have time to flow around it. The atoms in the air molecules hit the ball and mix with its atoms. Gamma rays appear. They break molecules apart. The air around the batter turns into red-hot plasma. The umpire and the catcher aren't to be envied either. Try to play baseball in volcanic lava. All this happens in nanoseconds. There's 1 billion nanoseconds in 1 second. The eyes and brains of people don't have time to analyze what's happening in front of them. The ball breaks into tiny pieces. Now it looks like a cloud of burning plasma. These are carbon, oxygen, nitrogen, and hydrogen. The stadium is engulfed in plasma and X-rays. For miles around, there's little more than a desert. The landscape resembles the surface of the moon or Mars. Let's take a look at it in slow motion. The bright light comes on first. Then a fireball appears in the middle of the stadium. Boom! The sound of the explosion reaches you. A pillar of fire bursts into the sky and turns into an eerie cloud that most resembles a colossal mushroom. Don't forget about the blast wave. It tears the trees out of the ground and knocks out all the windows in the vicinity. Thankfully, in the real world, such a situation is impossible. The International Space Station has enough problems without baseballs. Here's an American football field, and this is the ISS. The station weighs 420 tons. This is the largest spaceship ever built by humans. The large size and weight of 320 cars doesn't prevent the station from flying 5 miles per second. The ISS orbits the Earth 16 times per day. At this speed, any particle can pierce the hull of the ship or tear off one of its solar panels. There are 2,000 active satellites flying around the Earth. Another 3,000 don't work, but continue their space travel. And that's not all. In space, there are 100 million pieces of debris no larger than half an inch. And we sent them there. At least 34,000 particles the size of your smartphone and more. Even the smallest piece can destroy an astronaut's suit, equipment, or unprotected areas of the ISS. A single screw flying at 40 times the speed of a jet is a dangerous projectile, especially in space. Still, the ISS is safe. The padding protects it against impact with small objects. Now with larger ones, it's more difficult, but scientists have figured out how to deal with them too. A security perimeter has been created around the ISS. Imagine a pizza box 15.5 miles long and 2.5 miles wide. The space station is suspended in the center of the box, and its walls are the perimeter boundaries. NASA specialists record every violator of the space border. Scientists calculate the probability of collision. If it's dangerous, the ISS begins to maneuver and avoids the impact. In 2020, the station changed its flight route 3 times. Hundreds of objects enter the Earth's atmosphere every year. Most are burned before they hit the planet's surface. If the metal debris bursts through the atmosphere, it most likely end up in unpopulated lands or the ocean. Still, things happen. In the early morning of January 22, 1997, Lottie Williams was walking through a park in Oklahoma. In the pre-dawn sky, she saw a bright ball of fire. The woman decided it was a shooting star. Suddenly, she felt something touch her shoulder. It turned out to be a palm-sized piece of metal. The blow didn't harm Ms. Williams. She was the only person on the planet to have been hit by space debris. It was part of the fuel tank of the American Delta II rocket. The probability of getting hit by space debris is minimal. A huge kraken will sooner crawl into your room than a piece of a space satellite hitting you. Debris is invisible in the stream of thousands of small meteorites. They bombard the Earth's atmosphere every day. Most of the rocks are burned in it, and those that fall onto our planet are invisible. The only confirmed case of a close encounter with a meteorite was with Ann Hodges. In 1954, a space rock broke through the roof of a house and hit the woman in the thigh. The meteorite left a hole in the ceiling and a bruise on Ms. Hodges' leg. Let's imagine what would happen if an object the size and weight of a bowling ball flies toward our planet, naturally at the speed of light. In 2 seconds, our space object makes the distance from the moon to the Earth. The ball will crack, but we'll have time to start thermonuclear fusion. This process will release X-rays that will transform the atmosphere into a plasma bubble. It'll constantly expand. There will be no point of impact of space debris on the surface of the Earth. It won't have time to land, but it'll do a lot of nasty stuff. The explosion in the atmosphere will be colossal. The cataclysm will turn part of the planet into a lifeless desert and provoke the destruction of part of the Earth's crust. On the surface, fires, earthquakes, tsunamis, and volcanic eruptions will begin. The sun is the main source of light in our solar system. Light from the star reaches Pluto in 5 hours and 50 minutes. Mercury is only 3 minutes and 20 seconds away. As for Earth, 8 minutes and 20 seconds are enough. If we send a spacecraft to Mars tomorrow, it will reach its destination in 7 months. A rocket that travels at the speed of light will get it done in 3 minutes. We'll hardly ever learn to fly at the speed of light. Most modern spacecraft are powered by ion engines. But scientists are looking for an alternative. For thousands of years, people traveled by ships with sails. Today, this technology is relevant again. Engineers suggest using sails in space. They propose to catch the solar wind with them. A sail is installed on the spacecraft, and photons of light hit it. This creates pressure that pushes the object forward. The most ambiguous idea so far is to create an external pulsed plasma propulsion engine. Its principle is detonating hundreds of nuclear charges behind the spacecraft. The ship will fly forward on their shockwave. Thanks, but no thanks. The most sci-fi way to travel in space is to use a warp drive. In this case, we can fly faster than the speed of light. But first, we have to build an engine that distorts space-time and use this distortion for space travel. So far, this technology can only be found in movies and comics.
You're in the middle of the Sahara. You see a huge awning with a red target pattern. Its surface is so hot you could fry food on it. A drop of water is to hit the center of this target at the speed of light. Theoretically and technically, this experiment is impossible to conduct. But if it happens, then mysterious nothing awaits us. And each version of this nothing will be different. So we'll do 3 drops. Option 1. It's better to do it from a great height or space. You take off on a jetpack into the stratosphere. You have a bottle of water in your hand. You pour out 1 drop. Let's say it starts accelerating itself. In this case, even at a low speed, a drop of water will burn up in the protective layers of the atmosphere. In less than a second, the drop will turn to vapor. Let's say our planet had no such protection as the atmosphere. The air resistance would still get rid of the drop. The drop is flying down at a tremendous speed. The cold wind turns it into an icicle. The greater the drop velocity is, the stronger the air resistance is. The drop is moving faster and faster, soon reaching the speed of sound. Then, it just smashes into thousands of small particles. Under such conditions, the drop will never be able to reach the Earth at the speed of light. Nothing happens because nothing gets to the target. The next attempt involves changing the drop. Oxygen, carbon dioxide, ozone, and other gases in the atmosphere destroy any falling object. But what if the drop didn't meet all these obstacles? You change the internal structure of water chemically. So, you put your jetpack on again and grab a bottle of water. At the height of the Earth's orbit, you open it and pour out 1 drop. It accelerates and there's no resistance. It passes through the hottest layers of the atmosphere, but doesn't burn, passing the freezing temperature, but doesn't freeze up. It flies to the ground, developing the speed of light, and crashes again. But nothing happens. The drop got the properties of a light particle, a photon. It's only under such condition that it might develop the speed we need. No object with mass, be it a car, a house, a tree, an ant, a single air, a grain of sand, or a molecule, can reach the speed of light. Only light particles are capable of it since they don't have mass. An intangible drop falls into the center of the target, and again, nothing happens. The third option. Scientists found a way to accelerate a drop to the required speed. They also have to change the molecular composition of water, making it more resistant to high and low temperatures. To make the drop reach the speed of light without any damage, you need to place it in a perfect vacuum. No air resistance, no protective layers of the atmosphere. We leave only space and the water. For this purpose, scientists need to build a long pipe. In the center of the Sahara, around the same target, people create a scientific center. From here, the pipe should go up. Its height is approximately the distance to the International Space Station. That's 254 miles, which is about the height of 50 Everest mountains. You can't connect to the ISS itself as it's moving all the time. It revolves around the Earth, completing one revolution in 90 minutes. That's why astrophysicists and engineers should build a small station designed for one person. And this station should move parallel to a single point on the ground. The vacuum tube is made of solid stainless materials so that rain and high temperature couldn't destroy it. Inside, it's an alloy of titanium and graphene, the most durable metal on Earth. The pipe is built horizontally. Then, with the help of several helicopters and cables, it's placed in an upright position and attached to a small space station. The pipe is equipped with small pumps that pump the air out and block its flow inside. The water drop shouldn't touch the walls, so there's a special layer of gravity plates. They push the water away from the pipe's surface, using the power of magnetism and sound waves. You put on a jetpack and fly to the station with a bottle of upgraded durable water. Your hands are shaking with excitement. Your breathing sounds loud in the spacesuit. You open the bottle, tilt it slightly, and pour one drop into a special box. Inside this container, the drop gets charged with the energy needed to develop the speed of light. Now it's ready for the journey. You look at the box, close your eyes, and press the start button. The drop flies into the pipe at a great speed. From the powerful blast wave, the entire station is thrown to the side. The drop accelerates, and at this point, the pipe made of the strongest metals on Earth begins to melt like ice cream. There's so much energy in the water now that it would be enough to provide electricity to a small city. And now the drop reaches the speed of light, which is 186,000 miles per second. The pipe turns to dust. It doesn't matter whether the drop hits the ground or not, because there will be nothing. Literally, all material objects, cars, houses, fields, oceans, computers, planes, ships, flowers, trees, should I go on, will disappear. Intangible things, such as gas, air, radio waves, electromagnetic radiation, billions of terabytes of digital information, all this will also be gone. Boy, are you in trouble. Any sound, shouting, music, the phone ringing, will be impossible to create and hear. The light will disappear, and then there will be complete darkness. But let's rewind time and see exactly what happened right now. It won't work, though, because there's no time either. Imagine time as a stormy river that flows rapidly in one direction. Then this river falls into an endless pit and disappears completely. All this happened because a drop of water crashed into our planet at the speed of light. As soon as a drop begins to approach the needed speed, it loses its properties of water. It's now the most powerful and heaviest object in the universe. The energy that comes from it destroys everything for hundreds of thousands of miles. Concrete, ground, rocks, etc., 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 and on and on and on. Everything disappears. In the first second, it all gets shattered into millions of tiny pieces. Then these pieces are torn apart into millions of even smaller particles. The molecules burn up. Imagine a paper map of the world. If you wet it and tear it, it will turn into wet paper scraps. If you burn it, then part of the map will turn to ashes, and the other part will simply fly into the air in the form of smoke. The map will remain, but it will never look the same. But if you destroy the map's molecules, it's safe to say that the map never existed. There's no trace of its existence. The same thing happens to our planet. The energy coming from a drop of water makes the Earth never exist in space. And now the drop exceeds the speed of light. A black hole starts evolving. It expands and absorbs all the space debris. Then the Moon. Soon it will be the turn of Mars and all the other planets in our solar system. The black hole expands and increases the force of gravity inside it. Together with our planet, it absorbs light. It's getting closer and closer to the Sun. Our star splits into strips of light as if it had passed through a huge cosmic shredder. The Sun explodes and spits out an impossible amount of energy. It's believed that black holes appear after the explosion of stars. Right now, all the solar energy is being absorbed by our black hole. It's getting pitch black. The light from distant stars falls directly into the supermassive infinity. Meteorites flying within a radius of hundreds of thousands of miles around are also devoured into the unknown. There are many black holes in space, but only one of them was created by a small drop of water. The higher the speed of any object, the heavier it gets. Mass is the amount of energy that an object has. When water molecules reach the speed of light, their mass begins to grow, and there are no limits to this. It becomes infinite. An infinite mass forms a black hole. It absorbs everything, and nobody knows what's inside the black hole. All that remains is darkness and the unimaginable force of gravity. So, I'm guessing here that we probably should not be doing this experiment, should we? How about we make a baking soda volcano instead?
These days, we discover exoplanets that are thousands of light years away. We descend to the ocean's depths and conquer the highest peaks. We study quantum physics and build quantum computers. But for some reason, we still don't know about these strange lights in the night sky. Some of them are still unexplained. Some may turn into unexpected discoveries, and others are large-scale falsifications. Let's start with the most mysterious burning balls. These lights regularly appear near the town of Marfa in West Texas. These basketball-sized lights suddenly appear out of nowhere in the middle of the night. They flicker, split into two parts, and take off into the sky several times a year. For several generations, people have seen blue, white, yellow, and other lights. The existence of these lights is not some legend, but a fact confirmed by scientists, but they still need to explain its nature. A local shepherd first noticed Marfa lights in 1883. At first, he thought that those were the fires that Apaches had made. Neighbors told the shepherd that they had seen the mysterious lights too. They all decided to check the Apache theory, and it turned out to be wrong. There were no traces of a fire in the place the lights had been flying above. Then, in the 40s, pilots of the nearest Midland airfield saw the Marfa lights. They also wanted to figure out the secret of this phenomenon, but didn't find out anything. More and more people saw the bizarre lights. Many of them were sure that the lights had been some ships of an extraterrestrial civilization. Others said those were the souls of wandering spirits. But scientific theories seemed much more realistic. A group of physics students conducted their own investigation and found out that the lights were the headlights of cars passing on the nearest highway. Okay, some lights do look like headlights, but what about those that take off into the sky and change their colors? It may be an optical illusion that occurs when a layer of cold air presses on a warm one. You can observe the same visual effect in the ocean, when it seems to you that a ship is floating in the air on the horizon. But if these lights are headlights and an optical illusion, why do people see them only a few times a year? Another version of the light's origin suggests that they're something like swamp lights. You can see mysterious bright balls rising into the sky in the middle of the night. Organic substances such as twigs, leaves, and fallen trees decompose in wet areas and emit phosphine and methane gases. When these substances come into contact with oxygen, they ignite, but there are no such wet places in West Texas. Where could this gas come from? There are a lot of oil and natural gas reserves in the bowels of this region, and all these substances can contain phosphine and methane. It sounds realistic, but scientists have not confirmed this version yet. Aerospace engineer James Bunnell explained the nature of Marfa lights by an unusual electric charge. Solid substances such as minerals and various crystals generate electricity under pressure, and this underground energy bursts out in the form of multicolored lights. But the scientist couldn't prove his theory. Marfa lights are still a mystery. Perhaps you can solve it. Other lights surprise people in Norway in the city of Hessdalen. Hessdalen lights, unlike other similar phenomena, can often appear in the night sky. And of course, people have recorded them on camera many times. From 1981 to 1984, Hessdalen lights appeared 10 to 20 times a week. Now, people observe them from 10 to 20 times a year. These giant balls float in the air, pulsate, flash, and move very fast. Also, the balls can hang in the air from a few seconds to several hours. Even though people recorded them on camera many times, scientists still cannot study them. Hessdalen lights are very bright, and if people understand their nature, they can create light sources using this unknown alternative energy. So far, there are several theories about these lights. Physicists suggest that the balls appear when clouds of dust containing scandium burn in the air. It's a light silver-colored metal. There are many deposits of this substance in the valley where people observe Hessdalen lights. Another theory says that the balls are the result of the accumulation of macroscopic crystals in the dust plasma. This plasma is formed when air is ionized and blah blah blah. In short, this is a complex scientific hypothesis that hasn't been confirmed. Scientists need a lot of funding to study Hessdalen lights. Researchers try to attract investors by saying that the mechanism of Hessdalen lights can encourage a technological leap in light-based technologies. Some of the most famous lights in the world appeared in Phoenix, Arizona in 1997. Tens of thousands of people saw two strange phenomena that day. The first was a giant flying triangle. At about 8 p.m., several lights appeared in the sky, lined up in a triangle. They flew in an even formation through Phoenix and disappeared far into the sky. The second phenomenon started about 2 hours later. People noticed lights hovering in the sky. They didn't form a triangle and moved freely. They burned with a bright light, flew in different directions, and disappeared behind a mountain range southwest of Phoenix. People were scared. They called the police and reported strange lights. Many were sure that those were ships of an extraterrestrial civilization. But the explanation soon appeared. Both incidents were the result of aircraft exercises. In the first case, people saw several planes lined up in a triangle. They flew over Phoenix and landed at an air base nearby. In the second case, exercises were held using lighting rockets. Several planes dropped glowing rockets, which were landing on tiny parachutes for a long time. They burned in the air and then disappeared behind a mountain range. Quite a logical explanation, but then, almost 10 years later, something strange happened again. On April 21, 2008, the Phoenix police station received hundreds of messages from worried residents who had seen strange lights in the sky. 4 bright balls hovered over the city, changing their shape. They became triangular, then rectangular, and then disappeared one by one. The police contacted the nearest airfield, but they said that the radar hadn't seen any objects in the sky. If those had been material things, the radar devices would have shown them. The police had no explanation. The air traffic controllers also didn't know what it was. The case caused a great stir in society. Many began to recall the phenomenon that occurred a decade ago and again claimed that those were extraterrestrial ships, but all disputes ended after 2 days. Some man called local television and admitted that he had created the lights using flares and helium balloons. He tied a flare to a balloon, set it on fire, and lifted it into the air. Then, minutes later, he repeated this action, then again, 4 times. Many witnesses of the lights didn't believe this story and continued to insist on the extraterrestrial nature of the mysterious balls, but they were wrong. Radars would have noticed something if objects with a metal surface had been flying there, but light balloons and flares were too small to be detected by radars. Secondly, all the lights were flying to the east. The wind was blowing in the same direction that day. Third, the time of the burning. Signal rockets burned for about 20 minutes. When one of those lights faded, the second burned down for another minute. And the last one went out about 20 to 30 minutes after the first fire was started. Witnesses mentioned the same duration of time. One of the locals was a neighbor of the guy who confessed to organizing the hoax. The neighbor saw him lighting flares around 8 p.m., at about the time when the calls to the police started. Phoenix lights have become a great example of how easy it is to deceive people and cause a stir.